When you are first learning the Denavit-Hartenberg method, it can feel like it's a difficult, complicated, or obscure method, but really it just takes some practice to get used to what each of these parameters means and start to become skilled at seeing the parameter values in the diagram. The way to do this is just to get some practice. In this video, I'm going to give you a bunch of examples of finding the Denavit-Hartenberg parameter table for our standard manipulator types. In a previous video, we assigned the frames to each of the standard manipulator types according to the Denavit-Hartenberg rules. So I'm not going to go back over that again. Instead, I'm going to start with the frames we've already assigned and find the parameter table. Here, I'm starting with the Cartesian manipulator. In my table, I need to have 4 columns. The first 2 columns are for our rotational or angular variables, theta and alpha. And the other 2 columns are for our linear variables, r and d. I need to have 1 fewer row than I have frames, and I have 4 frames here, so I need to have 3 rows. Let's start with theta. Theta is defined as the rotation around Zn-1. It has to include the part of the rotation that's due to the joint variable, and also any additional rotation that's needed to get the xn-1 axis to match the xn axis. So in row 1, I'm looking at the difference between frame 0 and frame 1. I have no rotation due to the joint variable because this is a prismatic joint. However, I do have some rotation that is required to get frame 0 to match frame 1. When I'm trying to find theta, I want to pay attention to the difference in the 2 x-axes. Here, x0 is pointing into the page, and x1 is pointing up. In order to get x0 to match x1, I will need to rotate frame 0 around z0 like this in this direction, and I'll have to rotate it 90 degrees to get x to go up. Because of this, the value of theta in my table will be 90 degrees. Let's try and find theta for the second row. Once again, I have no theta rotation that is due to the joint variable because this is a prismatic joint. So the next thing I want to do is to compare the 2 x-axes of the frame. So x1 is pointing up and x2 is pointing to the right. In order to get these 2 x-axes to match, I would have to rotate frame 1 around z1 90 degrees. So theta in this row of the table will be 90 degrees. Let's do theta for the third row. We have no theta due to the joint variable because our third joint is also prismatic. So the next thing I do is I look at the directions of the 2 x-axes. x2 is pointing to the right, and x3 is also pointing to the right. So there isn't any theta rotation that is needed to get these 2 axes to match. Theta for the third row is 0. Let's do alpha. Alpha is defined as the amount of rotation that we need to rotate frame n-1 around the axis xn in order to get the 2 z-axes to match. So let's try and find alpha for the first row. Z0 is pointing to the right, and Z1 is pointing into the page. So I need to ask myself, how much do I need to rotate the 0 frame around the axis x1, like that, in order to get Z0 to match Z1? Now, this is a place where many people get stuck, because it's hard to remember that the frame that we're rotating is frame 0, not frame 1, even though the axis we're rotating around is the x1 frame. Sometimes it can be easier to look at the n-1 frame, in this case frame 0, and identify which axis is in the same direction as x1. Here, y0 is in the same direction as x1. So another way to think about this is that I'm trying to rotate frame 0 around y0, which is in the same direction as x1, to get z0 to match z1. Here, I would have to rotate frame 0 90 degrees to get z0 to point into the page, the same way z1 is. So that means that alpha for the first row is 90 degrees. Let's try and find alpha for the next row. To find alpha for row 2, I want to first identify the directions of the two z-axes. Z1 is pointing into the page, and Z2 is pointing down. I want to ask myself, how do I have to rotate frame 1 around the axis x2 in order to get Z1 to match Z2? I might want to start by finding which of the axes in the 1 frame is in the same direction as x2. And here I do have one of those axes, y1. How do I have to rotate frame 1 around x2, or y1, which is in the same direction, to get z1 to point down the same direction as z2? I only have to rotate 90 degrees, but there's kind of a catch in this case. The 90 degrees that I have to rotate here is in the negative direction. If I would rotate in the positive direction 90 degrees, I would get Z1 to point up. But I want Z1 to point down to match Z2. So I have to rotate negative 90 degrees around x2 in order to get Z1 to point down. So alpha in the second row is negative 90. The last alpha value is easy because these two frames already match each other. Z2 and Z3 are both already pointing down, so I don't have to rotate frame 2 around x3 at all. Let's do the R parameter. R is defined as the distance from the center of the n-1 frame to the center of the n frame in the xn direction. The xn direction here is up. The center of 0 and the center of frame 1 are lined up in the x1 direction. So here, R is 0. Let's look at R for the second row. We want to find what is the distance between the center of frame 1 and the center of frame 2 in the xn, or in this case, the x2 direction. Once again, these two frames are lined up perfectly in the x2 direction, so R is 0. Let's look at R for the third row. We want to find the distance from the center of frame 2 to the center of frame 3 in the xn, in this case x3 direction. These two frames are lined up perfectly in the x3 direction, so R is 0 here too. Alright, moving on to the D parameter. D is the displacement from the center of frame n-1 to the center of frame n in the Zn-1 direction. Here we have two components to the displacement. We have the link length A1, and we also have the joint variable D1. In practice, when we actually build this manipulator, A1 would be defined as the distance between these two joints when our joint has not been extended at all. So if this joint is, let's say, a belt drive, or a lead screw, or maybe it's a rack and pinion, A1 would be the distance between these two joints when we have homed the axis. That's why the distance between these two frames is A1 plus D1. It's equal to the distance between the two frames when the joint is 0, that is A1, plus however much the joint has moved. That's what D1 is. Let's do the next D. D for the second row is the distance between the center of frame 1 and the center of frame 2 in the Z1 direction. Once again, this has a component that is the link length and also a component that is however much the joint has extended. So D for the second row will be A2 plus D2. Let's do the last one. D in the third row is the distance between the center of frame 2 and the center of frame 3 in the Z2 direction. Just like the other two, this has a component that is the link length plus a component that is the joint variable. So D in the third row is A3 plus D3. We want to take a moment to check our work. At the end of this video, we'll be checking our work more closely by putting this parameter table into our Python code and computing the homogeneous transformation matrix. But for right now, let's just look at our table and make sure that all of our link lengths show up in the table, and all of our joint variables also show up in the table. If we ever have something in our kinematic diagram that really does affect the position and or orientation of the end effector, but doesn't show up in our table, that would mean we'd made a mistake. But here we have A1, A2, and A3 in our table, and we also have D1, D2, and D3. So it looks like for now we're probably correct. We'll check this more later. For now, let's move on to the next example. Let's do the articulated manipulator. This is our kinematic diagram, which we drew previously. I've already drawn my table to have its 4 columns and 3 rows since we have 4 frames. We need 3 rows. Let's start by doing theta. Theta is the rotation around Zn-1 that we need to get frame 0 to match frame 1. In particular, we're going to include any joint variable that we might have as a rotation around Zn-1, and we also want to look at the difference between the two x-axes. Here, we do have a rotation due to the joint variable. Theta 1 is a rotation around Z0. So I need to include theta 1 in my first row for theta. Next, I want to look at the difference between x0 and x1. These are pointing in the same direction, so I don't need any additional rotation of theta to get these two x-axes to match. That means we're done with theta for the first row. Let's do theta for the second row. Here, we also have a rotation that is due to the joint variable. Theta 2 is a rotation around Zn-1, which in this case is Z1. So we need to have a part of theta that is theta 2. Next, we look at our two x-axes. x1 is pointing to the right, and so is x2. So we don't need any additional rotation around Z1 to get these two axes to match. That means that theta 2 is all we need in this row of the table for theta. Lastly, when we compare frame 2 and frame 3, it looks like my frame 3 is missing an axis. Y3 is actually pointing up here. In theta for the third row, we do have a part of the rotation that is due to the joint variable. Theta 3 is around Zn minus 1, which in this case is Z2. So I do have to have theta 3 here. Next, we look at the two directions of the x-axes. In this case, they are also pointing in the same direction, so I don't need any additional rotation for theta. Let's move on to the alpha column. Alpha is defined as the rotation around xn that is required to get axis Zn minus 1 to match Zn. So the first thing that we do to find alpha is we want to identify the directions of the two z-axes. Z1 or Z0 is pointing up and Z1 is pointing out of the page. Now we're going to rotate frame 0 around xn, which is x1, in order to try and get these two z-axes to match. In order to get Z0 to be pointing out of the page the way Z1 is, I would need to rotate frame 0 around x1 90 degrees. That means that alpha for the first row is 90. Let's do alpha for the second row. When finding alpha, we first identify the directions of the two z-axes. Z1 is coming out of the page, and Z2 is also coming out of the page. Because of this, alpha for this row will be 0. I don't need to rotate frame 1 at all in order to get the z-axes to match. So alpha in the second row is 0. When we get alpha for the third row, it will also be 0 because the two z-axes, Z2 and Z3, are also in the same direction. Let's do the R column. R is defined as the distance or displacement between the centers of the two adjacent frames along the xn direction. So to find the first row R, we're going to look at the displacement from the center of frame 0 to the center of frame 1 in the x1 direction. These two frames are lined up perfectly in the x1 direction, so R in the first row is 0. To get R for the second row, we'll look at the displacement from the center of frame 1 to the center of frame 2 in the xn direction, which here is x2. The displacement between the centers of these two frames in the x2 direction is a2. So I write A2 for R in the second row. Lastly, to get the third row for R, we'll look at the distance or displacement from the center of frame 2 to the center of frame 3 in the x3 direction. This distance is A3. Let's do the D column. D is the displacement from the center of the n-1 frame to the center of the n frame in the Zn-1 direction. Here, this distance is A1. For the second row, we'll look at the displacement from the center of frame 1 to the center of frame 2 in the Zn-1, that is Z1 direction. These two frames are lined up perfectly in the Z1 direction. So D in the second row is 0. This is also the case for the third row. The displacement between the center of frame 2 and the center of frame 3 in the Z2 direction is also 0. Before we decide that we're done with the table, we want to check to make sure that all of our link lengths and all of our joint variables show up somewhere in the table. And I see that they do. we have A1, A2, and A3, and also theta 1, theta 2, and theta 3 in our table. We will check the accuracy of our work more in a moment when we put this into our code. For now, let's do the next example. I'm going to skip the Scara example because I did that in the last video. Instead, I'm going to move right along to the spherical manipulator example. Here I've drawn the kinematic diagram for the spherical manipulator. Remember that when we assigned the frames according to the Denavit-Hartenberg rules in a previous video, we learned that we had to move the 2 frame back onto the center of the second joint from where we originally drew it and the center of the third joint in order to obey all 4 of the Denavit-Hartenberg rules for assigning frames. So in this diagram, I've drawn the 2 frame in orange and the 1 frame in red to help you see the difference between them. The centers of these 2 frames are actually in the exact same location. Let's go ahead and fill out this table. Theta is defined as the rotation around Zn-1. This has to include both the joint variable, if there is a rotational joint variable, and also whatever additional rotation is needed to get the 2 x-axes to match. For the first row, I do have a part of the joint variable because theta 1 is a rotation around Z0, and in this case, 0 is my n-1 frame. So I do have a part here that is theta 1. Do I have a second part here? To find out, I have to compare the directions of the 2 x-axes. x1, or x0 rather, is pointing to the right, and x1 is also pointing to the right. That means that I don't need any additional rotation for theta to get these 2 axes to match. And I'm done with theta for the first row. Next, let's do theta for the second row. Here, I also have a joint variable component because theta 2 is a rotation around x1, which is my n-1 frame in this case. So I have to have theta 2. To find out if we have any additional component, I have to compare the directions of x1 and x2. x1, shown in red, is pointing to the right. x2, shown in orange here, is pointing up. So I have to ask myself, how do I have to rotate frame 1 around the axis Z1 in order to get x1 to match x2? I would have to rotate 90 degrees around Z1 to get x1 to point up, the same direction as x2. So I have to add on 90 degrees to theta in the second row. Let's do theta for the third row. Here, I do not have a component due to the joint variable because the third joint is prismatic, so it doesn't have a rotational joint variable. But I do still have to think about the directions of the x-axes. x2 is pointing up. x3 is also pointing up. That means that I don't have any theta rotation that is needed to get these 2 axes to match. Since I have no component due to the joint variable and no component needed to make the 2 axes match, theta in the third row is 0. Let's move on to alpha. Alpha is the rotation that I have to rotate frame n-1 around axis xn to get the z-axes to match. So to figure this out, the first thing I do is identify the directions of the 2 z-axes. Z0 is pointing up, and Z1, shown in red here, is pointing out. I want to figure out how much I have to rotate frame 0 around the x1 axis to get z0 to match z1. I would have to rotate frame 0 90 degrees around the x1 direction in order to get z0 to point out the same way that z1 is. So alpha in the first row is 90. Let's find alpha for the second row. The first thing we do is identify the two z directions. z1 is pointing out towards us, and z2 is pointing to the right. So I have to ask myself, how do we have to rotate the one frame around the x2 axis in order to get that z1 to match z2? The x-axis is pointing up, so rotating around the x2 axis in the positive direction would be like this. In order to get z1 to be pointing to the right like z2 is, we would have to rotate frame 1 90 degrees around x2. So alpha in the second row is 90 degrees. Let's do alpha for the third row. z2 is pointing to the right, and z3 is also pointing to the right. So we don't have to rotate frame 2 around x3 at all in order to get these two axes to match. Alpha in the third row is 0. Let's move on to r. R for the first row asks us, what is the displacement from frame 0 to frame 1 in the xn direction, and xn here is x1. The centers of these two frames are lined up perfectly in the x1 direction, so r in the first row is 0. Next, we'll do r for the second row. For the second row, r is asking us what is the displacement from the center of frame 1 to the center of frame 2 in the x2 direction. This is easy since the center of frame 1 and the center of frame 2 is actually in the exact same place. There is no displacement at all between frame 1 and frame 2. So r in the second row is 0. I could even fill in d for the second row right away also, since we've just noticed that the displacement between the center of frame 1 and the center of frame 2 is 0 in any direction. D in the second row will also be 0. Let's look at r for the third row. To find r for the third row, we want to look at what is the displacement from the center of frame 2 to the center of frame 3 in the x3 direction. There is no displacement between the center of frame 2 and the center of frame 3 in the x3 direction, so r in the third row is 0. Let's do the d parameter. D for the first row is asking us what is the displacement from the center of frame 0 to the center of frame 1 in the zn-1, that is z0 direction. This displacement is a1. We already filled in d for the second row, so let's do d for the third row. D in the third row is asking us what is the displacement between the center of frame 2 and the center of frame 3 in the z2 direction. Here we have quite a bit of displacement. We have the link length A2 and the link length A3. And we also have the joint variable D3. We need to make sure we include all of these. D in the third row is the sum of all three of these components. Now we'll look at our table and make sure that we've included all link lengths that we have and also all joint variables. I see that we do have theta 1 and theta 2 and D3, and we have A1, A2, and A3. So for now, our table looks good. We'll move on. The last example I'm going to show is the cylindrical manipulator shown here. We'll start with theta. Between frame 0 and frame 1, we have theta 1, the joint variable, that has to come into play with the theta parameter. So I'll write theta 1, since that has to be at least part of this parameter. Next, I'll take a look at the two x directions. x0 is pointing to the right, and x1 is also pointing to the right. So I don't need any additional rotation to get these two axes to match. So I'm done with theta for row 1. Now, theta for row 2. Here I'll be looking at frame 1 and frame 2. Because the second joint is a prismatic joint, we don't have any theta variable due to the joint variable. I only have to take a look at the two x-axes. x1 is pointing to the right, and x2 is pointing into the page. So I have to ask myself, how do I have to rotate frame 1 around the axis z1 in order to get x1 to match x2? If I rotated 90 degrees around z1, x1 would point into the page. So theta in row 2 is 90 degrees. Theta for row 3 also does not have any component that is due to the joint variable, because the third joint is also prismatic. So I'll take a look at the two x directions. x2 and x3 are pointing in the same direction, so there is no additional rotation that is needed to get these two axes to match. So theta for the third row is 0. Let's take a look at alpha. To find alpha, I first identify the two z directions. z0 is pointing up, and z1 is also pointing up. So there is no rotation needed to get these two z-axes to match. Alpha is 0. Next, let's find alpha for the second row. I'll identify the z directions for frame 1 and frame 2. z1 is pointing up, and z2 is pointing to the right. So there is going to have to be some rotation to get these two to match. So I'll ask myself, how do I have to rotate frame 1 around the x2 axis in order to get z1 to match z2? I would have to rotate frame 1 90 degrees around the x2 direction in order to get z1 to be pointing to the right. So alpha for the second row is 90. Now let's do the third row. z2 is pointing to the right, and z3 is also pointing to the right. So there is no rotation needed to get these two axes to match. Alpha for the third row is 0. Now we'll move on to the r parameter. To find r for the first row, I'll ask, what is the displacement between the center of frame 0 and the center of frame 1, measured in the xn direction? N here is 1. The centers of these two frames are lined up perfectly in the x1 direction, so r for the first row is 0. To get r for the second row, we'll look at what is the displacement between the center of frame 1 and the center of frame 2, measured in the x2 direction. Once again, these two frames are lined up in the x2 direction, so r for the second row is 0 also. Lastly, we look at the displacement from the center of frame 2 to the center of frame 3, and we want to find this displacement in the x3 direction. Once again, these two frames are lined up in the x3 direction, so r for the third row is also 0. Finally, we'll do the d column. D in the first row is asking us, what is the displacement from the center of frame 0 to the center of frame 1, measured in the z0 direction? This value is a1. Now we do the second row. D in the second row is asking what is the displacement from the center of frame 1 to the center of frame 2, measured in the Z1 direction. This displacement has one part that is due to the link length, and we also have a joint variable here. Those are both in the Z1 direction. So D in the second row will be A2 plus D2. Finally, D for the third row is asking what is the displacement from the center of frame 2 to the center of frame 3 in the Z2 direction. Similar to the second row, this displacement has a link length component and a joint variable component. The total distance between the center of frame 2 and the center of frame 3 in the Z2 direction is A3 plus D3. Now I want to look at my table and make sure that I have all joint variables showing up somewhere in my table. I do. I have theta 1, D2, and D3 all showing up. Also, I have to make sure that all of my link lengths show up. A1, A2, and A3 all show up in my table, so that looks good for now. Let's check our work by computing the homogeneous transformation matrix and looking at what the numbers are in the homogeneous transformation matrix for certain values of the joint variables. Instead of doing this by hand, we'll do it in our Python code, and we'll do it in the next video.